So in this lecture, I'm going to give vector representation of angular displacement, angular velocity, and angular acceleration. Before this, you should keep a point regarding this angular displacement theta bar. Angular displacement is a vector only for small angles, infinitesimal rotations. Infinitesimal rotation means 1 degree, 0.01 degree, zero point 0.2 degrees, like that. Very, very small rotations. For small rotations only, angular displacement is a vector. And same thing is applicable even for angular velocity also. Angular velocity also is a vector for small angular displacements only. This thing you should keep it in mind. For larger finitesimal angular displacement is not a vector, but infinitesimal angular displacement is a vector. That is observation number 1. So what is the first observation? Only small angular displacements are vectors. Larger angular displacements are not vectors. Same thing is applicable for angular velocity also. This is observation number 1. And observation number 2, all these theta bar, that is angular displacement, angular velocity, angular acceleration, if you want angular momentum and torque, all these are axial vectors. What is that? Axial vectors. What do you mean by axial vector? I'm not giving you the proper definition, but all these axial vectors are pointed in the direction of axis of rotation, that is namely axis of rotation. So with respect to that particular axis only, we can define these angular parameters, whether it is angular displacement, angular velocity. That's why these vectors are called axial or pseudo vectors. Axial or pseudo vectors, because to define the direction we need the axis of rotation. They always point either in the direction of axis of rotation or opposite to the direction of axis of rotation. That I'm going to discuss here clearly. For that purpose, to understand what is the angular displacement, again I'm going to consider here a circle. So to understand the direction of angular velocity, I'm considering here a circle in which a particle is rotating in counterclockwise sense, that is in this sense. In such a case, what you should do is to find the direction of angular velocity. First, you decide what is r bar. Let me call it as this is r bar. And at this instant, velocity, tangential velocity is in this direction. This is the direction of velocity. Okay. Now, so when the particle is moving in this circular path, I'm considering the instant when the particle started at A and it moved to another position B, like this B. Okay. In this sense, in this case, what is the direction in which the particle is moving? Along this curve. Along this curve, it is moving like this. Okay, this length I am taking it as dl. Okay, so to find out the direction of angular velocity, we should use right hand grip rule. This is my right hand. Okay, what you should do? You should curl the fingers in the direction in which the particle is rotating. This is rotating in counterclockwise sense, because of which my right hand I'm using, and I'm curling my fingers in the direction in which the particle is rotating. Then the direction in which this thumb is pointing, that is the direction in which the angular displacement is directed. Did you understand this? I am repeating it one more time. If the particle is moving on the circle in counterclockwise sense, what you should do? We should use your right hand. Okay, so we should curl our fingers in the direction in which the particle is rotating. So this so I am curling my fingers in counterclockwise sense. Then my thumb is pointing towards the observer, that is in upward direction. So here the axis of rotation will be the center of the circle. So here if you imagine an axis like this, okay, now from this right hand grip rule, what I can say, as I curl my fingers in the direction, in the sense in which the particle is rotating, my thumb is pointing in parallel to this axis, which is this pair, the direction in which this pen is pointing. This is the axis. So this thumb direction and this axis direction both are parallel to each other. So here what I can say is angular velocity or angular displacement is pointing in upward direction, towards the observer, in upward direction. So the direction of angular velocity is in upward direction. So to represent it vectorally, what I'm doing is this direction I'm taking as positive x direction, this right direction I'm taking it as positive x direction, and this upward direction I'm taking it as y direction. Then in this direction, vertically upward direction, that is going to be z direction. Z direction is vertical upwards. By using right hand grip rule, I decided it. Okay, so if you take I cap is the unit vector along the x direction, and j cap is the unit vector along the y direction, and vertically upward direction, that is along the z, I am taking it as k. That I am representing here it by a dot over here. Dot represents vertically upward and cross represents vertically into the plane of the paper. Okay, that convention I am using here. So angular velocity is pointed in the direction of k cap. Okay, angular displacement is pointed in the direction of k cap. That I'm trying to put it in vector sense. So before that, just now I wrote this expression. What is that? D theta, angular displacement d theta is equal to, what I wrote it as, ds divided by r. Actually ds is also a vector, am I right? Ds, displacement along this curve, is a vector, and r bar also a vector, but there is nothing like vector division. Okay, I'm going to use one technique. I will multiply both numerator and denominator with r. Then what I will get? ds into r divided by r square. So this I will try to convert it into a vector, because just now I figured out by using right hand grip rule, d theta should be in which direction? K cap direction. So I am putting it here, k cap is equal to, okay, what kind of product should I take between ds and r? Okay, because both ds and r are lying on the plane of the paper, and d theta is perpendicular to the plane of the paper. That means I should define cross product it, whether I should take ds bar cross r bar or r bar cross ds bar. For that purpose I am going to use this vector identity. What is that? If you want to get k cap, what product should I take? In which sense I should take the cross product between I and j? If I define I cap cross j cap, I will be getting k cap. So right hand side I want to get k cap. So I should define what is that? I cross j. So here what is the vector which is pointing in the direction of I? That is r. So because of which I am writing it like this: r bar cross remaining vector should be ds bar divided by r square. Did you understand this or not? Because here at this instant ds bar is pointing in which direction? In I cap direction, and r bar is pointing in I cap direction, ds bar is pointing in j cap direction. So I cross j will be k, because of which I can write it as d theta bar now. So the direction of angular displacement d theta bar in vector form, I can write it like this. Therefore d theta bar is equal to 1 divided by r square into r bar plus ds bar. Okay, in a similar way you can write down the expression for angular displacement also. That is omega bar is equal, which is nothing but rate of change of angular displacement. Angular velocity, angular displacement, both of them will point in same direction. So here d theta bar is along k cap direction, means omega bar also should be along k cap direction, because of which I can write it as 1 by r square, because we know in scalar form v is equal to r omega, and omega is equal to v divided by r. That I am using here. So this also, in a similar way as angular displacement, we can write down angular velocity as 1 by r square into r bar cross, what is that? V bar. This is the relationship between the angular velocity and tangential velocity in vector form. You better remember this. Okay, so I am going to justify this by using what you call it as right hand grip rule, one in terms of angular velocity also, because linear velocity at this tangential velocity at this instant is in y direction. So in the sense in which the particle is rotating, I am curling the fingers. Okay, the thumb is should point in the direction of angular velocity, because r bar cross v bar, from r to v I am curling my fingers. This is r to the right, and in the direction of v I am curling my fingers. Then my thumb is pointing in k cap direction. So because of which I wrote it as omega bar is equal to 1 by r square into r bar cross v bar. Okay, this is how I represented vectorly. Okay, next thing is regarding angular acceleration alpha bar. In vector form I am going to represent here. So in scalar form we know that what is that, a is equal to, what is this a, be careful, this is tangential acceleration is equal to r alpha, we know this. Through this angular acceleration alpha is equal to what you can write, tangential acceleration at divided by r. That I am going to represent it in vector form, because angular acceleration is a pseudo vector, so it is a fact based formula only. There is no derivation for this. I searched for so many books, but nowhere you can find these expressions. Okay, so this also I can write it as 1 by r square into, okay, what you can write it as, alpha is equal to at divided by, I put one r extra because of which you can write it as r bar cross at bar, r bar cross at bar. So be careful, whatever it may be, the direction of r bar cross at bar is alpha bar. Here you should be very careful, because at can be either in upward direction or in downward direction, whereas velocity can be in upward direction only when the particle is moving in counterclockwise. For same counterclockwise direction, at can be either upward, tangential acceleration can be upward or downwards. So if the particle speed is increasing, at will be in the direction of v bar, because of which angular acceleration, if velocity of the particle is increasing, then what happens, at and v bar are parallel. So because of which, as the particle is moving in counterclockwise sense, in this case alpha direction will be in the direction of k cap. If at and v bar both are anti-parallel, this happens in which case, if the speed of the particle is decreasing. If at and v bar are anti-parallel, then alpha will be in which direction, angular acceleration will be in which direction, angular acceleration will be in minus k cap direction. That is, when the velocity of the particle is increasing, what is happening, angular acceleration is pointing in upward direction. When the particle is decelerating, tangential acceleration is in downward direction. Here I am showing it, tangential acceleration is in downward direction. So r2, now I am twisting my right hand like this, r2 at, you should curl your fingers. Then what happens, this thumb is pointing in downward direction, that downward direction I am taking it as opposite to k, which is minus k cap direction. So while deciding the direction of angular acceleration, you should be very careful whether the acceleration of the particle, whether the velocity of the, whether the speed of the particle is increasing or decreasing. If it is increasing, then it is in k cap direction. If it is decreasing, it is in minus k cap direction. So whatever I discussed so far, you should do it in reverse sense, when if the particle is rotating in clockwise sense. Okay, so these are the relationship between the angular parameters and linear parameters in vector form. This is in scalar form. So these relations are very, very important and useful while solving the problems. Alternately, we can write these expressions like this also. Tangential velocity v bar is equal to, in reverse sense I am writing. Here I wrote omega in terms of r and v. Now I am writing v in terms of omega and r bar. V is in which direction in this diagram? V is in j cap direction. So if you want j here, you should take k cross I. What is k? Omega bar. So that only I am writing here. V bar is equal to omega bar cross r bar. In a similar way, angular acceleration alpha bar is equal to what I can write? Tangential acceleration at bar cross r bar. Alternatively, we can write down the expressions like this also.